Hello, good evening, everyone. Welcome back to another session in this late night series in the subject of fluid mechanics. I'm Vikas Sir. I welcome you all to this session on boundary layer. And I'm really sorry, first of all, that the session got delayed by this much time. Uh, Actually, I was having a very problem in my laptop. Because of that, the class was not able to start. So I'm really sorry about this thing. The session got delayed by this time of 14 minutes. Hi, good evening, Vikas Yadav. Good evening, Naveen. Good evening, Akhilesh. Good evening. Hi, Raju. Chalani, very good evening. Rishabh Yadav, good evening. Ayush Sharma, good evening. So, very good evening to all of you and welcome to this session. And very sorry that the session got delayed by this much time. So, everyone, welcome to this session. I hope you guys are doing fine and very good evening to all of you. Today in this session, we'll be studying about the concept of boundary layer, which is a very important concept of the subject of fluid mechanics. Hi Sabir, very good evening. Hi Abhishek Kumar, good evening. Welcome to the session. So good evening all my dear students. Welcome to this session. Today in this session, we'll be covering the concept of the boundary layer subject. Boundary layer, which is an important topic of the subject of fluid mechanics. So I hope you guys are ready for this topic, for understanding this topic. The last lecture that we have covered was on the Reynolds and Freud model law, which comes under the dimensional analysis, in which we have solved many questions. I hope you all have understood that topic. Hi Shivani, good evening. So good evening all of you and welcome to this session. I hope you guys are doing fine and I hope you are enjoying this late night series. And today, this session got delayed for some time because of some technical issues with my laptop, and it is causing some issues from last few days, which, as you all know. So today, basically, I was not able to open my laptop because of some issues. I don't know what they were. So really sorry, and let's begin the session without any delay now because we have to start this very important topic of boundary layer. Before we begin, I have to introduce myself. I'm Vikas Sir. I have 5+ year teaching experience. I did my MTech in thermal engineering from Thapar University and I have mentored more than 10,000 plus aspirants for different exams like GATE, Engineering Services and SSC. My area of expertise includes subjects of fluid mechanics, thermal and applied and heat transfer subject. So that is a small introduction about myself. Now I think this is very helpful. Okay, thank you so much for enjoying this session and I hope this series is helpful for all of you. Okay, so let us begin the concept of boundary layer. What is boundary layer? What do you meant by boundary layer? Okay, so I will cover some important basic fact about the boundary layer. Okay, what is the meaning of this boundary layer thing? Okay, that is all we have to cover today. And in the end, we'll be solving some numericals on this topic of boundary layer. Okay, so let us start this amazing topic of the boundary layer and boundary layer theory. Right now, let us say that what is the meaning of this boundary layer? What is the meaning of this term boundary layer? Let us say we are having a fluid. Let us say we are having a fluid, and this fluid is basically normally it is flowing on it is flowing in a free stream. Okay, let us say our fluid is flowing like that. This is a fluid flowing on this is also called as free stream. What is the meaning of free stream? The fluid is flowing like this. This is a free stream. It is flowing simply, right? Let us say the water is flowing in the river, the water is flowing in a canal, or water is flowing in a pond, something like that. So it is a free stream. Okay, it is not in contact with any other surface. What is the meaning of fluid as free stream? What is the meaning of fluid as free stream? The free stream is defined as it is the fluid flowing which is not in contact, which is not in contact with any surface. The fluid which is flowing, which is not in contact with any surface, or basically it is free stream. Okay, it is not affected by the viscous forces. It is only affected by the viscous forces between the fluid. It will not be in contact with any surface. That is called as free stream. Hi, good evening, Shivam Singh, Rupendra, very good evening, Kalam, good evening, Lakshmi, Prasanna, very good evening. So what is the meaning of, what is the meaning of free stream? It is a fluid which is not in contact with any surface, or it is flowing without any contact with external surface. That is called as free stream. Okay, like you feel yourself free when you say that I am feeling very free, right? Because I don't have any obligation or something like that. You call yourself free, right? Similarly, a free stream means it is not in contact or touch with any surface. It is simply in contact with the fluid particles. It is simply in contact with the other fluid particles. Okay, so if a fluid is only in contact with the fluid particles, it is not in contact with the surface, then that is called a free stream. Okay, now I will be denoting, let's say the velocity of free flowing stream is u infinity. Let us say we are denoting the velocity of free stream, flowing stream as u infinity. That is how we are denoting the velocity of free flowing stream. Now, my dear students, this is one scenario. Another scenario is that we are having a surface. Okay, and let us say this is a flat surface. Okay, this surface is fixed. Now over this surface, the free stream is flowing. The free stream was flowing. Okay, suddenly what happens in the path of the free stream? It experiences that there is a surface which is coming like this. The fluid was flowing very freely. It was not having any, contact with any surface. Suddenly, what happens? Suddenly, in front of the free stream, we are having a surface. We are having a surface, or let us say a flat surface is there. Let us say we are having a flat surface and the fluid is flowing freely, but it comes in contact with a flat surface. So what will happen? You have studied in the Newton's law of viscosity that when the fluid particles will eventually come in contact with this surface of the flat surface, then what will happen? Initially, the fluid particles are having the free stream velocity u infinity. Let us say it is free stream velocity, free, right? We are denoting by u infinity. Okay. So, but as the fluid particles will come in contact with the plate, when they will contact with the surface, then what will happen? Some fluid particles which are in contact with the plates, they will cling to the surface. The fluid particles which are exactly in contact with the surface, they will cling to the plate. Okay, this flat surface, let's say. So they will cling to the plate. Cling means attached. They feel like they're attached to the plate. Now this flat surface is having no velocity. Velocity was 0 here. Now there is a property called as no slip condition. What is the meaning of no slip condition? No slip condition is a condition when the fluid particles which are flowing over a surface, their velocity becomes almost equal to that surface. That is called as no slip condition. So under no slip condition, the velocity of the fluid, the local velocity of the fluid, that is velocity at this particular point, the local velocity of the fluid will become 0 at y is equal to 0. Y means the distance away from the free surface, the distance in perpendicular direction to the flat surface, that distance is y here. We sometimes also call it as distance from pipe wall. Okay, so that means the velocity at the flat surface of the fluid will be 0. Why? Because the fluid particles will feel like they are in contact, or they have been clinged together with the surface. Okay, so the fluid particles feel like the clinged to surface. Okay, so under that situation, what will happen? The velocity will become 0. Okay, now what will happen? as the fluid particles will move away from the surface, you will notice a very strange thing. The strange thing will be some fluid particles which are in immediate contact with the flat surface, they will be having up to certain height, the velocity will be increasing. Up to certain height, their velocity will be increasing away from the surface, and they will come a point when their velocity will become equal to free stream velocity, or almost 0.99. Use this pen. Okay, so they will come a point when the velocity will become equal to the free stream velocity. Okay, after traveling some certain distance, the velocity, yeah. Anurag Bharti saying use this pen, sir. Which pen, Anurag? So the velocity will become equal to almost 0.99 times of free stream velocity. So you will, if you basically, you will get a point on this at the point where the velocity will become 0.9 of free stream velocity, and up till here, you will find that there will be some velocity gradient which will be formed. There will be some velocity gradient which will be formed, that is the velocity, the fluid particles will move with relative velocity. Okay, clear? So that means velocity at this particular point, if it is u, the velocity here will be equal to u plus du. Okay. This session contains additional topics of FM. So Mantra, no, this topic only contains, this lecture only contains boundary layer topic. Okay. So the fluid particles which are just away, or the just adjacent fluid particles above this will be having more velocity, that is, this is a relative velocity u plus du. So as this fluid, as you move away from the surface in perpendicular direction, you will find that the velocity will be increasing in the perpendicular direction away from the surface. And there will come a point after some point when this velocity will become equal to or almost equal to or almost 99% times of free stream velocity. Clear? And because of that, what will happen? Because of that, you will be getting a point at this, you will be getting a point. That point will be, basically it will be a locus of boundary layer. Okay, so let me draw the diagram again here. So my dear student, basically I was telling you that we are having a fluid. Let me draw a bigger diagram. We are having a fluid which is a free stream velocity. So when this flows over a surface, then initially what will happen, there will be some velocity gradients which will be formed. Okay, initially the fluid particles will stick to the surface, but after that what will happen, the some fluid particles will be basically have the relative velocity. The velocity will be more as you go away from the surface, and there will come a point when this velocity will become almost 99% of the free stream velocity, almost it will become equal to the free stream velocity. Okay, there will come a point when this velocity gradient will become 0, and after that there will be only this type of flow. The fluid will move again with the free stream velocity. Okay, so what I want to tell you here is, this will happen every time when a fluid will flow over a surface. Then in a very close boundary, in a region close to the surface, there will be some velocity gradient. There will be some velocity gradient up to this point. There will be some velocity gradient will be formed. Velocity gradients will be formed in a perpendicular direction. Okay, near to the surface. After covering a particular distance away from the surface, flat surface, what will happen? This velocity gradient will become 0, and the fluid velocity, that is the velocity of the fluid, local velocity of the fluid here at this point, the local velocity of the fluid will become equal to 99% of free stream velocity. That is almost become equal to free stream velocity, this velocity of the free stream. Okay, clear? And the thickness up to which, the distance away from the flat plate up to which this velocity gradient will be there, that is called as boundary layer thickness. That thickness of the boundary up to which this boundary layer, this velocity gradient will be there, will be called boundary layer thickness. Clear? The distance away from the plate up to which this boundary layer, this velocity gradient will be there. That is, velocity gradient means change of the velocity if you go in the perpendicular direction away from plate. So these velocity gradient will be available only up to a certain distance. Okay, clear? Clear everyone? Is the line velocity gradient? So this will be the velocity gradient, we can say. Let me draw it with different pen. Let us say this is the velocity gradient. This is with the velocity gradient. You can see that if you move away from the surface, the velocity is increasing. Okay. At the surface, the velocity will be zero at this point, because this surface because the fluid is flowing over a flat surface which is stationary. This surface is stationary. You can simply imagine this thing. Our river water is flowing. Suddenly a river comes across the surface, over a river water has to flow over a surface. Then what will happen? You will notice, you won't be able to notice it, but it will happen that in a very near to the surface, in a very basically there will be a thickness, there will be distance up to which this boundary layer will be formed. What is this boundary layer? So the point where the velocity will become free stream velocity, you will be getting a point. In the similar manner, what will happen? In the similar manner, the fluid will be flowing further. You will be getting a different point here. Okay, you will be getting another point here. When the velocity will become almost equal to free stream velocity, you will be getting a point. So this is one point, this is another point, this is another point. So if you join this locus of the point, what you will get? You will be getting this kind of layer. Okay, you will be getting this kind of layer formed over the surface. If you join the locus of the point, locus of fluid flow at different points where local velocity u becomes 0.99 times of free stream velocity. If you join the locus of the point, this point, this point, this point, you will be getting a layer like this. This layer, my dear, this imaginary layer is called as boundary layer. Okay, I will tell you everything about the boundary layer, don't worry. Clear? Above boundary layer thickness, the velocity will be same as the free stream velocity. It will become almost same, 99% close to the free stream velocity, and after that it will flow with the same free stream velocity, same. It will be u infinity after later on. Okay, clear everyone? That means it has been noticed that when the fluid particles come in contact with the surface, when it flows over a surface, there will be some velocity gradient up to a certain point, up to certain length, up to certain height away from the plate. Velocity gradient means there will be variation of the velocity, and after a particular thickness, after a particular distance, which is called boundary layer thickness, this velocity gradient will be zero. That means at this point du by dy will be zero. Okay, when velocity of the fluid will become equal to free stream velocity, 99% of free stream velocity, the velocity gradient becomes zero. Okay, now I know what are your doubts. I will tell you later. Just wait for 1 minute. So let us say we are having this boundary layer growth. Okay, this is a kind of boundary layer which is formed here. Okay. Now, my dear student, this is, let us say, this is your boundary layer. This is your boundary layer. A layer above the surface. Now you must be thinking, what will happen outside the boundary layer? So this is the reason outside boundary layer, and this is the reason inside boundary layer. So inside boundary layer there will be some velocity gradient like this. There will be some velocity gradients like this. Okay, these will be some velocity gradients like this inside the boundary layer. And if you join the points of velocity gradient where u becomes 0.99 times of u infinity, okay, you will be getting this value of, this thickness will be equal to boundary layer thickness. Okay, this will be boundary layer thickness. Why point of free stream velocity is different at different position? Because as the fluid particles will move in this direction, the boundary layer thickness will grow. As the fluid particles will move in this direction, x direction, the boundary layer thickness will increase. It increases in this direction. That is why if you join the points of, if you see the velocity gradient, this boundary layer thickness will also grow because the boundary layer thickness is a function of x. Okay, as the fluid will move along the free surface, along this surface, the boundary layer will also grow over the surface. Okay, so what will happen outside the boundary layer? Outside boundary layer, the velocity gradient will be zero. The velocity gradients will be zero. Also, there will be no effect of viscosity. No effect of viscosity. So we can say that the fluid will be almost inviscid. Inviscid means having zero viscosity. Also one more thing, the shear stress will become zero because shear stress is equal to mu du by dy. Outside boundary layer, outside the boundary layer, the shear stress will be zero. Okay, because the velocity gradient will be zero outside boundary layer. Okay, clear everyone? One more thing, inside boundary layer, shear stress mu is equal to du by dy will be there. Why? Because velocity gradients are there, and where velocity gradients are there, shear stress will be there. So there will be shear stress acting inside boundary layer, not outside boundary layer. Okay, so outside boundary layer, what will happen? The shear stress will be zero. Okay, one more thing, inside boundary layer, the fluid particles will be rotating about its axis. They will be having rotation about its axis inside boundary layer. So we can also say that the flow is rotational. Flow is rotational inside boundary layer. Inside boundary layer, the flow will be rotational. And outside boundary layer, flow is irrotational. Outside boundary layer. Okay, so we can also say that just above the outside boundary layer, the fluid will try to behave like an ideal fluid. Okay, because an ideal fluid is what? It is incompressible, it is irrotational, it has no viscosity, right? So we can say that outside boundary layer, the fluid will behave as ideal fluid. It will behave as an ideal fluid outside the boundary layer because it will be having no viscosity. It will almost become inviscid. It will be irrotational. Okay, that is, these are all characteristics of an ideal fluid. Clear everyone? So outside boundary layer, the fluid will behave like an ideal fluid. It will be having no shear stress, no velocity gradients. Velocity gradients will be zero, shear stress will be zero, and the flow will be irrotational outside boundary layer. Clear? So these are some questions which comes in the exam many times. That what happens the velocity gradient outside the boundary layer, what happens to the shear stress outside boundary layer. Okay, these are some questions which commonly asked in the exam. Clear everyone? So inside boundary layer, we'll be having this velocity gradient, we'll be having the rotational flow of the fluid, okay, and we'll also having the effect of shear stress inside the boundary layer. Also, at the wall surface, the fluid particles which are immediately near the wall, they will be having the shear stress, which is also called wall shear stress, which is mu times of du by dy at y is equal to 0. The shear stress, is it applicable for air? See, we are talking about the fluid, Dharni Krishna. We are talking about the fluid which is incompressible fluid. Okay. So yes, the effect of boundary layer will be for air also. It is not that it will not be for air, because outside boundary layer the fluid will be incompressible, but inside boundary layer the fluid can be compressible also, right? So this boundary layer phenomena can happen for both compressible fluid and incompressible fluids. Okay, clear everyone? This boundary layer phenomenon is also experienced by aeroplanes, your automobiles, your cars, your motorcycles. Okay, that is why the design of your car, we do some special designing of your car. Why? In order to suppress the boundary layer. Why the aeroplanes have been designed with that special shape? In order to reduce the boundary layer effects. Or in order to reduce the effect of boundary layer separation. You will come to know what is boundary layer separation. Okay. So that is a very important thing about the boundary layer. Now I have to tell you about a very important things. The boundary layer conditions. The boundary layer boundary conditions. These are very, very important. Try to understand it very carefully. What are these boundary conditions? Let us say we are having this boundary layer growth like this. Okay, now as I have told you that the thickness of the boundary layer, if you move in this direction, the thickness of the boundary layer will increase. If you go in this direction, the thickness of the boundary layer will increase. Okay, so the thickness of the boundary layer, this is the defined as thickness of boundary layer. Thickness of boundary layer is a function of x. It is a function of x. If you go in this direction, as the fluid will move in this direction, the boundary layer thickness will increase. Okay, the boundary layer thickness will increase like this. So that means the boundary layer thickness at this point, at this point, at this point, at this point, that is delta 4 will be greater than delta 3, it will be greater than delta 2, it will be greater than delta 1. So boundary layer thickness will grow as we go in this direction. But what is the relation between the boundary layer and this movement of the fluid over the surface? What is the relation between them? That relation I will tell you. It depends on the fluid, whether it is laminar or turbulent. Okay. So my dear, I have to tell you about some boundary condition. What are the boundary conditions? See, these boundary conditions are very, very important. First boundary condition is at u is equal to 0. Sorry, at y is equal to 0, u will be equal to 0. Y means the distance from the wall, distance from the plate. What is the meaning of y? Y means the vertical distance or vertical perpendicular distance away from plate, away from flat surface. Okay. So at this particular condition, when y will be 0, at this particular point u will be 0. This is also called as no slip condition. So this condition will be applied. This is a no slip condition. How much height it can grow, I will tell you the height of boundary layer, don't worry. This height is nothing but it is called boundary layer thickness. Okay, my dear Baldev. Okay, so at y is equal to 0, u is equal to 0. Second condition is that at y is equal to delta. That means when this boundary layer thickness will be completely formed at y is equal to delta, u will become almost 0.99 times of free stream velocity. Also, at y is equal to delta, du by dy, that is velocity gradient, will be 0. Now these three boundary conditions are very, very important. That is, the first one is when y is equal to 0, u will be 0. This is called no slip condition. At y is equal to delta, that means when this y becomes delta, at this particular point, u will become 0.99 times of free stream velocity. At this particular point, u will become 0.99 times of free stream velocity. This is the point of 0.99 times of free stream velocity. If you join this point of 0.99 times of free stream velocity, if you join them with a line, imaginary line, you will be getting our boundary layer. you will be getting our boundary layer. This is how the boundary layer will grow. Okay, so how the boundary layer has been formed? Boundary layer has been basically formed by joining the locus of the point of the local velocity. When local velocity becomes 99% of free stream velocity, if you join those points, you will get a layer over a surface. That layer is called, that imaginary layer is called as boundary layer. Clear everyone? Are this boundary condition clear? Yes, please tell me, my dear students. Are this boundary condition clear or not? Now I am going to tell you a very important thing. When can we say that the flow will be laminar or turbulent? When can we say the flow will be laminar or turbulent in a case of a boundary layer growth? For example, in the case of a pipe flow, when Reynolds number is less than or equal to 2000, we call it as laminar flow. When it is greater than 4000, it is called turbulent flow. So what will be the condition for flow over a flat plate? So let us understand that. Let us say that we are having a flat surface. And this is how the boundary layer is growing like this. Let us say then suddenly we'll be having this kind of line, then we'll be having the, in turbulent region we'll having this kind of, this is how the boundary layer will grow in the turbulent region. In the turbulent region, so let us say the flow is taking place on a flat surface. This is a flat surface. What is the effects of boundary layer? See, the effects of boundary layer I will tell you. I am going to tell you what is the effect of boundary layer, Kiran Kumar. The effects of boundary layer are displacement thickness, which is reduction in the mass flow rate. Momentum thickness, which is a reduction in the momentum of the fluid. Energy thickness, which is a reduction in kinetic energy of the fluid. So this is the effect of boundary layer. I will tell you what is the effect of boundary layer. Okay, don't worry. So let us say we are observing the flow of the fluid over a flat plate. So let us say initially this is a flat plate, this is a flat plate, this is a flat plate, and we are studying the growth of a boundary layer growth over a flat plate. Okay, clear everyone? Now my dear students, it has been observed that when the fluid will flow over a flat surface, after a particular distance, after traveling a particular distance, this side of the plate will be called as leading edge. This is called leading edge of the plate. Leading means over which the flow will start. It is called leading edge. The end point will be called as trailing edge. Trailing edge means the last point of the plate over which the fluid is flowing. It is called trailing edge. The starting point is called leading edge. Okay, my dear students. Now, so when the flow will start over this flat plate, what will happen? At the leading edge, what will happen? We can say that from the leading edge up to the point here, we'll be having a laminar flow. Okay. After some point, what will happen? We'll be having a transition region. This is called transition region. It is also called transition flow. And after that, after this transition region, we'll be having this region that is called as turbulent region. This is called as turbulent region. Okay. Any practical example of use of boundary layer theory? Yes, there are many practical examples of the boundary layer. The boundary layer growth you can observe over what we call a tennis ball. On a tennis ball, why they are providing this? What we can say that they are providing some dimples over the tennis ball. Why they are basically, if you see the aeroplane, why the blades of the aeroplanes have been designed like a aerofoil shape? What is the reason behind that? Right? In the case of a venturimeter, why the divergence angle is not allowed to go beyond 7 degree? Why it is less than 7 degree? In venturimeter, why the divergence angle is less than 7 degree? So there are many examples to understand the boundary layer. There are many practical examples. You have seen the car bodies. Have you seen how the car bodies have been designed? Every car has a particular design. Lamborghini will be having different design, BMW will be having different design. A sports car will be having some sleek design, a very good sleek design, right? But if you see a Wagoner, a normal commercial vehicle, you will find that it will be having a normal design of a car. Or even if you see nano car, you will see that design are not that much, a perfect curvy design is not there, right? So why the design of those cars is like that? It is somewhat related to boundary layer. I will tell you it is related to boundary layer. Okay. So my dear, from the start point of the leading edge up to the point where laminar flow will take place, that is called as, this region will be called as laminar flow region. This is called laminar flow region. And in this region, the velocity profile will be, or we can say the velocity gradients will be there. The boundary layer will be formed. Clear? But what is the point after which the flow will become turbulent? What is the point when the flow will become turbulent? From the starting to this point, the value of the Reynolds number will be called as critical Reynolds number. It is called critical Reynolds number. So what is the meaning of critical Reynolds number? Critical Reynolds number is that number after which the flow will start to change from laminar to turbulent. Okay. So when the fluid will flow over a particular length of the plate, after crossing a particular length of the plate, the flow will start to change from laminar to turbulent. So that value of Reynolds number at which the flow will start changing from laminar to turbulent, that is called critical Reynolds number, and that value is equal to 5 into 10 power 5 for a flat plate. For a flat plate, for a flow over a flat plate, the value of critical Reynolds number, critical means yes, it is critical because after crossing that Reynolds number value, the flow will start to change from laminar to turbulent. For example, in case of a flow over a pipe, in case of flow in a pipe, what is critical Reynolds number? Critical Reynolds number is equal to 2000. It is 2000 for flow in a pipe. Critical Reynolds number for a flow in a pipe is 2000 because after crossing the value of 2000, the flow will start changing to turbulent flow, right? But in the case of flow over a flat plate, the critical Reynolds number is 5 into 10 power 5. That means after Reynolds number will cross this value, the flow will start changing to turbulent flow. That means when Reynolds number becomes greater than 5 into 10 power 5 and less than 10 to power 7, this range is called as transition region. This is called transition region of the, or this is the region where transition will start. And in this region, when Reynolds number will become greater than 10 power 7, it will be called as turbulent flow. So we can say that, what is laminar stability? Lochin Sharma, I am telling you about this thing that I hope you understood the concept of the critical Reynolds number because that is very important. Okay. Laminar stability, we can simply say that in the case of a laminar flow, we know that there is a very high difference between laminar and turbulent flow. The difference lies in the form of how the fluid particles will flow. Okay. Laminar flow is a highly viscous flow, while turbulent flow is a flow which is having more velocity than less viscosity. Okay. So in the reason in a flow over a flat plate, the point up to which the Reynolds, the flow will be laminar, that is called critical Reynolds number, and that is 5 into 10 power 5 for a flow over a flat plate. But for a flow in a pipe, it is 2000. Clear? Now, you must notice one more important thing. What is the value of transition? See, it is a transition region. Because it is a transition region, there will not be any separate value of the value of the Reynolds number. It will be variable. It will lie between 5 greater than 10 power 5 into 10 power 5 and less than 10 power 7. So transition means lying between these two things. It will lie between the laminar flow and turbulent flow Reynolds number. No, that is not the range, Rupesh, my dear. The range of the transition region is why it is called transition. Transition region will start as laminar flow will end, it will the transition region which will start, and as the turbulent flow will start, the transition region will end. So the region between end of the laminar flow and start of the turbulent flow, that region is called transition region. Okay, clear everyone? Now if you notice here one more thing, the boundary layer thickness is more. In case of turbulent flow, the boundary layer thickness is very high. This boundary layer thickness is more in the case of turbulent flow as compared to laminar flow. Why it is happening? Why in the turbulent region the boundary layer thickness is more? What is the reason behind that? Or we can say why boundary layer is growing in the turbulent region as compared to laminar region. What is the reason behind that? What is the reason between sudden jerk between what this is not a sudden jerk, basically simply we can say that there is a range of transition you can see the range of Reynolds number. The range of the Reynolds number between laminar and turbulent flow is that much. It is between 5 and 10 power 5 and 10 power 7. It is not a sudden jerk, basically you can say that. It is the region that I am showing here. The region is this transition region. It is not a sudden jerk. This is the region which I am saying it is a transition region. Up to this point, the flow will be laminar. After that, the transition region will start. Okay. So let me understand important three things are important. One is displacement thickness, in a momentum thickness, and energy thickness. See, these are the three parameters. These are the mathematical terms in order to understand the effect of the boundary layer. The effect of the boundary layer can be understood by these three parameters: displacement thickness, momentum thickness, and energy thickness. These are all mathematical terms which are used to signify the effect of boundary layer. Okay, or what is the effect of boundary layer? That can be well understood by these three types of thickness. What is the meaning of these three thickness? So let me make you understand the meaning of this three thickness. So let us say the boundary layer is growing over a flat surface like this. Okay. Now it has been observed that inside the boundary layer region, the velocity gradients will be there, right? There will be some velocity gradient like this, right? And outside the boundary layer region, what will happen? The fluid will flow with the free stream velocity. This is the ideal fluid which is flowing here. The ideal fluid is flowing here. This is the ideal fluid. I just told you that outside boundary layer the fluid will behave like an ideal fluid. So let us say this is the ideal fluid which is flowing here. Okay, the ideal fluid is flowing here. This is how the ideal fluid flows. Okay, there will be no velocity gradients here. This is how the ideal fluid will flow. This is the ideal fluid. So ideal fluid is having no velocity gradient, it is flowing with a free stream velocity. Now what we'll observe here, my dear students, try to observe it very carefully. Boundary layer curvature is a streamline. No, it is not a streamline. The curvature of the boundary is not, it is not a streamline or what. How do we get the curvature? How we have got this boundary layer? The shape of the boundary layer. The shape of the boundary layer we have found by joining the point of that point where the velocity will become equal to 0.99 times of free stream velocity. Okay, so for different points, if we join the points of where velocity becomes 0.99 times of free stream velocity, when you join this point, you will be getting this imaginary layer that is called as boundary layer. Okay, so basically we have at different extent of time, we have joined the point of that point where the velocity becomes 0.99 times of free stream velocity. When you join these points, you'll be getting this layer that is called boundary layer. Okay, so what will happen? What is happening actually inside the boundary layer region? Because of the formation of this boundary layer over the surface, what happens? It is noted that as the boundary layer will grow over the surface, some fluid particles will try to enter into the boundary layer. Some fluid particles from this ideal fluid will try to enter into the boundary layer. So as the flow will proceed over the along the flat plate, it has been noticed that mass flow rate, at this point the mass flow rate will be different, and at this point the mass flow rate will be different. So as we move, as the boundary layer will grow, as the boundary layer grows, the fluid particles outside boundary layer will lose some fluid particles which goes inside boundary layer. Okay, and because of that, what will happen? Because of that, the mass flow rate of the fluid particles inside the boundary layer, the mass flow rate will increase. The mass flow rate inside the boundary layer will increase. As you go inside the boundary layer, the mass flow rate increase, and we can say that mass flow rate inside boundary layer increases, and mass flow rate of fluid outside boundary layer will decrease. Boundary layer decreases. Now this effect takes place when the boundary, some of you were asking me, sir, what is the effect of the growth of boundary layer? The main effect of the growth of boundary layer is that when the boundary layer will grow over the surface, then some fluid particles will try to enter into the boundary layer from the main stream flow, and because of that the fluid particles inside the boundary layer will have an increase in the mass flow rate, and the fluid particles outside boundary layer will have decrease in the mass flow rate. Now if you see this, my dear student, this is a region of ideal fluid region. This is the ideal fluid. So we can say that because of the boundary layer region, because of the growth of boundary layer, the mass flow rate of ideal fluid will decrease continuously because of boundary layer. There will be decrease of mass flow rate of ideal fluid. Right? So what is the meaning of displacement thickness? What is the meaning of displacement thickness? Displacement thickness come to the rescue here. What is the meaning of displacement thickness? So displacement thickness tells you that if we somehow displace our flat plate, let us say this is the boundary layer growth, let us say this is like this. If we somehow, this is the boundary layer which is formation take place. Okay, now because of this boundary layer formation, what is happening? There is a decrease in the mass flow rate. So what does displacement thickness tells you? If we shift our boundary layer, if we shift our flat surface, if we shift the flat surface here, okay, outside boundary layer, if we shift the flat surface here, okay, let us say this is our flat surface. If we shift our flat surface here like this, what will happen? If this is your flat surface, what will happen? If we shift our flat surface by some distance, rather than making the flat surface here, if we can shift the flat surface by some distance, so that this loss of mass flow rate can be avoided. If we can shift the mass flow rate, then what will happen? There will be no boundary layer growth, and the fluid will grow like this. The flow will be an ideal fluid. There will be no in order to compensate for loss of mass flow rate of ideal fluid, we can shift the surface by a distance. Let us say this distance here by which it is shifted is this delta star. This distance by which it is shifted is called as distance delta star, called as displacement thickness. The distance by which the boundary layer, this flat surface has to be shifted in order so that we can compensate for the loss of the boundary layer. That distance by which this flat surface have to shift it for basically compensating the loss in mass flow rate in the ideal fluid. That distance is called as the displacement thickness. Okay, very similar to this. What is momentum thickness? Momentum thickness means the distance by which flat surface should be shifted in order to compensate, because if there is a loss of, if there is decrease of mass flow rate, if there is decrease of mass flow rate of ideal fluid, there will be decrease of momentum also. There will be decrease of momentum also. Why? Because what is momentum? Momentum is equal to mass into velocity. So if the mass flow rate will be compensated, if mass flow rate will decrease, momentum will also decrease because of boundary layer. There will be decrease of momentum also. Momentum of the fluid also. Clear? So in order to compensate for the loss of momentum, we compensate for loss of momentum in ideal fluid. In order to compensate for the loss of momentum in ideal fluid, the flat surface should be shifted by some distance, and that distance is called momentum thickness, which is denoted by theta or delta double star. Okay, and very similar to that, what is energy thickness? Energy thickness means the vertical distance by which, see my dear students, I have to teach you a lot of things. If you are having any query, you can ask me your question, don't worry. But let me just complete this, because I have to teach you about the drag force also. I have to teach you about a lot of von Karman equation, everything I have to teach you. And I am thinking of teaching you the boundary separation also, if you will be having some time. Okay, so if you are having some doubt, you can ask me. Let me just complete this. Let me just complete the theory first of all. The vertical distance by which the flat surface need to be shifted in order to compensate loss of kinetic energy of an ideal fluid. That distance by which the flat plate has to be shifted is called as energy thickness. That distance by which it has to be shifted is called energy thickness, that is denoted by delta triple star. Okay? No. I am not saying, see, it is simply just a comparison. It is just an experimental comparison that if we somehow shift that, if we have to avoid the boundary layer, what we can do? If we are just doing some compensation, because this much amount of loss has taken place. Okay, this much amount of loss has taken place in the mass flow rate. So if we can shift the flat plate to this distance, okay, if we have shifted the here, then what will happen? This, if we shift to here, it will be having a compensation of that mass flow rate, loss of mass flow rate will be compensating that, will be basically equating that. Okay, I'm not saying that we are actually shifting our flat plate to that distance. No, we are not doing that. We are just trying to compensate it. Compensation means whatever loss has been given, we can just fulfill it. We can just make the, we can just what we can say, that we can just give some compensation for the loss. So as a result of compensation, we are trying to basically compensate it by some distance. We are shifting our flat plate by some distance experimentally, not actually. Clear, everyone? That is a theoretical approach. That is all theoretical approach what we are doing here. So there is a formula for displacement thickness, energy thickness, and boundary layer thickness. Displacement thickness is equal to this. It is given by this formula. It is equal to 1 minus u over u infinity d in 0 to integral of dy. Let me just write with the formula of all these things. Displacement thickness. See, all these are very, very important. Displacement thickness. The question comes in the exam from this point. Displacement thickness delta star is equal to 0 to delta of 1 minus u by u infinity dy. You must be thinking, what is this u by u infinity? This is the velocity profile. This is a velocity profile, the kind of velocity profile which is developing inside the boundary layer. Okay, this is the velocity profile which is there in boundary layer. The velocity profile which have been developed in boundary layer, that is u by u infinity. This will be given in the question. Okay, I am just telling you that we are not actually shifting that. We are basically trying to do compensation. What is the meaning of compensation? If you have done a loss to, suppose by accident you have hit someone else's car, so what you have to do? You can give some compensation. What you can do is you can give some money for that. If you have by accidentally you have done that, right? So that some repair can be done. So it is just a compensation. We are not actually shifting it. We are doing something which is theoretical. It is all theoretical approach. Okay. Right now I don't have the time for this. Otherwise I would have derived this equation. Okay, I would have derived all this equation because I don't have time. Otherwise I would have derived this equation of displacement thickness. Okay, as some particles will come inside boundary layer, but some inner particles will also thrown out because area under boundary is constant. No, area under boundary layer is not constant. It is constant. See, boundary layer is continuously decreasing. We should not forget this fact. Boundary layer, as the flow will proceed in this direction along the fluid, the boundary layer will continue to increase. As the boundary layer will continue to increase, the loss of mass flow rate will be there, loss of momentum will be there, loss of kinetic energy will continue to do so. Okay, so this is a velocity profile. This will be given in the exam. This will be given in the exam, velocity profile. In similarly, momentum thickness, how energy momentum thickness will change? It is not changing. I am saying that if there is a loss of mass flow rate, because of the boundary layer, some fluid particles from ideal fluid will enter into the boundary layer. So there will be loss of mass flow rate. Loss of mass flow rate will be loss of momentum, because momentum is equal to mass flow rate, or we can say mass flow rate into velocity, or mass into velocity if we are finding momentum per second. So there will be loss of momentum per second also. Similarly there will be loss of kinetic energy per second. That is half m dot v square. There will be loss of, because if mass flow rate have been compensated, mass flow rate is reduced, so obviously momentum will reduce, kinetic energy will reduce. Both are related. They all are related. If there is a loss of mass flow rate, there will be loss of momentum, there will be loss of kinetic energy because of the boundary layer. They all are related, my dear. They all are related. Okay. So there will be loss of momentum, there will be loss of kinetic energy of the fluid because there is a loss of mass flow rate because of the boundary layer. Okay, so momentum thickness will be equal to momentum thickness delta, it is denoted by delta double star, or it is equal to theta. See, my dear students, we are here preparing for GATE exam, and this I am teaching you only for so that you can clear your exam in this very small time. I know this topic is something which is actually a very important topic for discussion, but we don't have that much time for discussion. We have to solve questions also, we have to complete theory also. If I have to teach you just boundary layer in 2 or 3 classes, I would have definitely taken that much time, because we don't have that much time, my dear. Okay, so try to understand it. Okay, we are having a time limit. Momentum thickness will be equal to 0 to delta of u by u infinity 1 minus u over u infinity dy. This is how you find the momentum thickness. And energy thickness is equal to, energy thickness can be found mathematically by using this relation. Delta triple star will be equal to 0 to delta of u over u infinity 1 minus u square over u infinity square dy. Okay, or you can say that it is equal to 0 to delta of u by u infinity 1 minus u by u infinity whole square dy. This is also the formula for energy thickness. You can write it in any way. Okay, always remember that u by u infinity is the velocity profile. Okay, so this velocity profile will be given to in the question. Sometimes they will write it like this: u by u infinity is equal to y by delta. This is called as linear velocity profile. Sometimes they will not mention the velocity profile. They will write the fluid is following the linear velocity profile. Linear velocity profile means this. So when the velocity profile will be linear, so let us find the displacement thickness. Displacement thickness will be equal to 0 to delta of 1 minus u by u infinity of dy. That will be equal to 0 to delta of 1 minus y by delta of dy. Okay, in that case this will be y minus y square by 2 delta, 0 to delta. You will put the limits, you will be getting delta minus delta square by 2 delta. This will be delta by 2. Okay, so this is how you have to solve the problems of momentum thickness, energy thickness and displacement thickness in the exam. So for this velocity profile, linear velocity profile, you have found the displacement thickness. Similarly, you can find the momentum thickness, my dear. Momentum thickness will be equal to, if the velocity profile is this, linear velocity profile, you will be getting this as 0 to delta of u by u infinity 1 minus u by u infinity of dy. If you put the limit, you will be getting this as 0 to delta of velocity profile is this y by delta into 1 minus y by delta dy. If you put the inside, you will be getting this 0 delta of y by delta minus y square by delta square dy. If you integrate this, you will be getting this y square by 2 delta minus y cube by 3 delta square 0 to delta. If you put the limits, you will be getting this as delta square by 2 delta minus delta cube by 3 delta square. This will get cancelled out, this will get cancelled, this will be delta by 2 minus delta by 3. This will be delta by 6. So this is how you will be applying this formula of momentum thickness, displacement thickness, and also you can find energy thickness in same manner. In the same manner you can find energy thickness also. Energy thickness will be 0 to delta of 1 minus u by u infinity of 1 minus u by u infinity whole square of dy. So if the velocity profile is this, u by u infinity is equal to y by delta, you can just put the values, you will be getting this value as 0 to delta of y over delta 1 minus y square by delta square dy. If you multiply, this will be equal to 0 delta of y over delta minus y cube by delta cube. Okay, if you further integrate, you will be getting y square by 2 delta minus y power 4 by 4 delta cube. If you put the limit, you will be getting this value as delta square by 2 delta minus delta power 4 by 4 delta cube. This will get cancelled, this will get cancelled. This will be delta over 2 minus delta over 4. So what you can observe from here, this value will be equal to what? 4, 2 delta minus delta. This will be delta by 4. Okay. So for the single velocity profile, linear velocity profile, for linear velocity profile, if they will ask you find the displacement thickness, momentum thickness, energy thickness for linear velocity profile, the displacement thickness is equal to delta over 2, the momentum thickness is equal to delta over 6, and energy thickness is equal to delta over 4. Now my dear students, if you clearly observe this thing, that the displacement thickness, momentum thickness and energy thickness, is there any relation between these three? Yes, the relation is, always remember that displacement thickness will be greater than energy thickness, and energy thickness will be greater than momentum thickness. Math more difficult? No, it is not difficult, my dear. It is very simple. It is simple integral. Okay. So displacement thickness will be greater than momentum thickness, and energy thickness will be greater than momentum thickness. So this is a relation that you will observe here. There is also one important term that can be asked in the exam, that is shape factor. They can ask you to find the shape factor also. What is shape factor? It is equal to ratio of displacement thickness. It is equal to ratio of displacement thickness over the momentum thickness. The ratio of displacement thickness over momentum thickness is called as shape factor. In this particular condition, displacement thickness is delta by 2, momentum thickness is delta by 6. If you solve it, this value will be equal to 3. Are you getting this value, everyone? Okay, so this type of question will come in your exam for sure. Okay, this type of question will come in your exam for sure. And whatever I have told you in this 1 hour and 20 minutes, it is not because 15 minutes we are late. So in 1 hour approximately, this is very, very important about boundary layer, about the displacement thickness, about the momentum thickness and all. Okay, now I'm going to tell you some important formula. These are some important formula. Now we'll be telling you shape factor. I have already told you it is equal to this von Karman equation. Von Karman equation is used to find the value of the shear stress. It is used to find the value of shear stress, or to be very precise, wall shear stress. It is used to find the wall shear stress. Okay, so for finding the wall shear stress for laminar and turbulent flow, if we have to find the wall shear stress, we can use the von Karman equation. So according to von Karman, momentum integral equation will be getting this value. That is tau naught by rho v infinity square is equal to d theta by dx. Okay. Now my dear students, in this equation I need a blank page. Let me just use that blank page. This equation, tau naught is called as wall shear stress. It is called wall shear stress. What is the meaning of wall shear stress? In the growth of the boundary layer, growth, if this is your boundary layer growth, the shear stress which is acting exactly near the flat plate, the shear stress at this particular point, this is called wall shear stress. This is T naught, tau naught, wall shear stress. And this value is equal to mu times of du by dy at y is equal to 0. So this wall shear can be found by using two relations. This is one relation for finding wall shear stress, and this is another relation for finding wall shear stress. The wall shear stress is equal over rho u infinity square is equal to d into theta by dx. Do you know what is this theta here? Do you know what is this theta? Theta here, theta is called as momentum thickness. So if they have given the velocity profile u by u infinity is equal to y by delta, you can find the value of theta. Theta will be delta by 6. If you can differentiate this, you will be getting some value. Okay, this is the single velocity profile. They can give you some other velocity profile. They will give you like this velocity profile. They can give you the velocity profile like this also. U by u infinity is equal to 3 by 2 of y by delta minus half of y by delta cube. They can give you the velocity profile like this. They can ask you to find the wall shear stress. So how can you find wall shear stress? So it will be equal to U is equal to U infinity 3 by 2 of Y by delta minus half of Y by delta Q. What is dx? Dx is the change of rate of, basically it is equal to d by dx of, it is equal to d by dx of momentum thickness. It is equal to d by dx of momentum thickness. X is the distance from leading edge. This distance from leading edge, what is the distance from the leading edge? This is x. Okay, clear? So if you find du by dy, it will be equal to u infinity 3 by 2 by delta. And if you find du by dy at y is equal to 0, other term will be 0. So this will be equal to, the shear stress will be equal to mu times of 3 by 2 u infinity by delta. So this will be the value of wall shear stress for this type of velocity profile. Okay, this is how you can find the wall shear stress for this kind of velocity profile. So either you can find the wall shear stress if velocity profile is given. If velocity profile is not given, you can use the von Karman equation. Okay. So in the von Karman equation, this is density, this is the free stream velocity, this is momentum thickness, this is distance from the leading edge. Now there are two more formulas that you have to remember. What is the drag force? Let me tell you what is drag force. Okay. Let me just take out a blank slide and tell you what is the meaning of this drag force term. It is also very important. Okay, let us understand what is the meaning of drag force. What is drag force, my dear? You must be imagining this thing, that is drag force is same as friction. So suppose your fluid, fluid is moving in this direction. Okay, suppose your fluid is moving in this direction, and we are having a flat plate here. We are having a flat plate like this. Okay, now because of this, because the fluid is moving in this direction with some velocity u infinity. Okay, now the because of the movement of the fluid in this direction, this plate, this flat plate will also try to, it will not try to move, but the fluid particles will try to move in this direction of the flat plate like this. Now in opposition to the motion, in opposition to motion of our fluid particles, in opposition to motion of fluid, opposition force or opposing force will be experienced. Opposing force will act, okay, over fluid. Opposition force will act over fluid. That is called as, that is drag force. That is called as drag force. For example, if this plate is moving in this direction, let us say the plate is moving in this direction, okay, and the fluid is also moving in this direction. So what will be the direction of the drag force? So drag force, first of all, let me tell you that drag force, if the fluid is moving in this direction, then the drag force will be exactly acting in which direction? It will be in the direction of the flow. It will be in the direction of the fluid flow. Okay. So because the fluid is this plate, let us say the fluid is moving in this direction, then drag force will move in the opposite direction. It will act in the opposite direction or in the direction of the fluid. Drag force will act in direction of fluid. Although it is opposing force, but you will experience that in direction of fluid. Suppose you are sitting on a motorcycle, at the back of motorcycle, and you are holding suppose you are holding basically some package. Let us say you are having something, you are holding something, and if the driver of the motorcycle is moving the motorcycle at a very high speed, then what you will notice, the motorcycle is moving in this direction. It is moving in this direction. And in the same direction, you will be experiencing a force. Okay, because you are sitting on the motorcycle, you are moving in this direction. You will experience a drag force which will try to move you back. It will try to move you back. You will feel opposition force. It will try to pull you back. The drag force will try to pull you back in the opposite direction. Okay, but the direction of the motion of the drag force will be in the direction of the fluid. The direction which the fluid is moving, that will be direction of the motion. Okay, so when you are riding your motorcycle, let us say the fluid is moving in this direction, the bike is moving, the bike is moving in this direction, the fluid is moving in this direction. So drag force will be acting in this direction. This is the direction of drag force. Okay, drag force will be in direction of motion of the fluid. It will be in direction of motion of the fluid. So because of the drag force, it will try to pull you back in the opposite direction. Okay, the direction which your bike is moving, in the just opposite direction, the drag force will try to pull you back. Now that drag force is the opposition force because of the fluid. It is the opposition force acting because of the fluid motion. It is not because of the surface in contact. Do not confuse with the drag force with friction. It is not friction. Friction is not drag force. Drag force and friction are totally different. Okay. Clear, everyone? Now there is a formula for the drag force. That basically you have to understand that this drag force will be of two types. One is called as skin friction drag. Skin friction drag. Okay, and this can be local. We can say local skin friction drag. Another is average or mean friction drag. Mean friction drag. Okay, it is of two types, local or mean. This is local skin friction drag is denoted by C. Coefficient of local skin friction drag is denoted by CDX, and the average is denoted by CD bar or simply CD. This is average or mean friction drag coefficient, we can say. Okay. So my dear, the drag force is equal to half of CD, that is the total drag coefficient, into rho density into area into U infinity square. This is the formula for drag force. Drag force is equal to average drag coefficient. Average drag coefficient. Average drag coefficient. Rho is the density of fluid. It is density of fluid. Okay, A is the area of over which over which the fluid is flowing. That is the area of that surface over which the fluid is flowing, and U infinity is the free stream velocity. Okay, and this is the formula for wall shear stress. The wall shear stress is equal to the skin friction coefficient, local skin friction coefficient, divided by 2 into rho U infinity square. This is the formula for wall shear stress. Okay, or we can simply say that wall shear stress is equal to drag force per unit area. Okay, the wall shear stress is equal to CDX by half into rho infinity square. If you divide by area, it will be getting as sorry. That is correct. Okay, clear, everyone? So these are the two important formulas that you have to remember. Now I have to tell you important these relation. This is called as Blasius equation. These are very, very important. The last topic, then we'll be solving some numericals. Okay, now I have told you how to find the displacement thickness. I have told you how to find the momentum thickness and energy thickness if velocity profile is given. What if velocity profile is not given? What if velocity profile not given? Then what you are going to do? Then how can you find the displacement thickness, momentum thickness, energy thickness? How can you find that? If the velocity profile is not given, then Blasius gave some equations from which you can directly find the value of displacement thickness, coefficient of drag, average coefficient of drag, and local coefficient of drag. For laminar flow, when Reynolds number is equal to 5 into 10 power 5, and when Reynolds number is greater than 10 power 7, that is for turbulent flow, the skin this boundary layer thickness is equal to, directly you can find it as 5x by root of Reynolds number x. What is this Reynolds number x? See, in a flow over a flat plate, I told you that this is a leading edge and this is a trailing edge. Okay, so if you move away from if you move along the leading edge, the distance x is defined as, x is some distance from leading edge, distance taken from leading edge of the plate. Okay, that is called as x. Suppose they can ask you to find the value of x at critical Reynolds number, of 5 into 10 power 5. What is the value of x at which critical Reynolds number take place? So you can find it by using the relation, because Reynolds number, critical Reynolds number is 5 into 10 power 5. It is equal to rho into V infinity into x by nu. So you have to simply, what is this x? You can find the value of x at which this critical Reynolds number take place. If you know the value of density, if you know the viscosity, if you know the free stream velocity, you can find the x. That is, what is the distance from the leading edge at which the critical Reynolds number will be there. This you can find, xc you can find from here. Okay, so what is the x? X is the distance from the leading edge, and the local, this Reynolds number is called local Reynolds number. This is called as local Reynolds number. Local Reynolds number means which varies with the distance. It is equal to rho V infinity into x by mu, or V infinity into x by nu. This is called as local Reynolds number. There is also a term called average Reynolds number, that is for the whole length of the plate, or whole complete length of the plate. Here x is 0, here x is equal to L at trailing edge. So for the whole length of the plate, the average Reynolds number will be equal to rho into u infinity into L by mu, or u infinity into L by nu. This is called as average Reynolds number, a total Reynolds number. Okay, so one is called as average Reynolds number, one is called local Reynolds number. Local Reynolds number means that Reynolds number which is varying with the distance from the leading edge. Okay, so this boundary layer thickness, this is boundary layer thickness. I told you that boundary layer thickness varies with the distance from leading edge. So boundary layer thickness is equal to 5 into x by root of Reynolds number. This is boundary layer thickness. Okay, clear everyone? Is it clear? Okay. Or you can also, somewhere you can see that 4.91 into x root of Reynolds number. Sometimes they will be using this also. So if you want, you can take it approximately as 5x also, no problem. It is almost same. Either you can take it as 4.94, I think 4.94 or 4.95 or directly 5x. Doesn't matter, both are same. And for turbulent flow, the boundary layer thickness is equal to 0.37x Reynolds number power 1 by 5. But this value is this value of turbulent flow is basically more of, you can say this you have to remember for turbulent flow, this is the value of boundary layer thickness. So we can say that the boundary layer thickness is directly proportional to root x for laminar flow. For laminar flow, the boundary layer thickness is directly proportional to square root of, it is directly proportional to square root of the distance from the leading edge, and it is inversely proportional to square root of the velocity of free stream velocity. So these are some important relations that you have to remember. Okay. Similarly, for turbulent flow, the boundary layer thickness is directly proportional to x power 4 by 5. Okay, so these are the two important relations that from which question can be asked, okay, in the exam. Clear? You can write, see, we write 4.94, 4.64, no, I think 4.91 or something like that is there. but approximately you can take it as 5x. If nothing is mentioned, you can take it as approximately 5 into x by this. Okay. So this is the relation that you have to remember for laminar flow. For laminar flow, this is the relation. And for turbulent flow, this is the relation of boundary layer thickness and distance from the leading edge. Okay. So how the question will come in the exam? They will ask you that in the laminar flow in the turbulent flow region, let us say, if the boundary layer thickness at a distance of x1 is equal to, let us say, 2 mm or 2 centimeter, let us say, the boundary layer thickness is given as 2 mm. What is the value of the boundary layer thickness? What is the value of boundary layer thickness as x2 is equal to 4 centimeter? They can ask you for laminar region. For laminar flow, what is the value of delta 2 boundary layer thickness at x2? So how can you find it? You know that delta is directly proportional to root x for laminar flow. So you can say delta 1 by delta 2 will be equal to root of x1 by x2. So you can find delta 2 as root of x2 over x1 into delta 1. You can find it from here. This will be root of 4 by 2 into 2 mm, right? So that will be 2 root 2. Clear? So in this way you can find the value of the boundary layer thickness for laminar region. Similarly, if they ask you to find it for turbulent region, for turbulent flow, the boundary layer thickness is directly proportional to x power 4 by 5. Okay, clear? How root of x? Because I just told you for laminar flow, delta is equal to 5 into x by root of Reynolds number, local Reynolds number. This is equal to 5 into x by root of rho v x by mu. This is equal to x by root x. If you multiply with root x in denominator and numerator, this will get cancelled out. So we can get that delta is directly proportional to root x. Similarly, for turbulent flow, delta is equal to 0.371 x by Reynolds number power 1 by 5. Okay. Local Reynolds number and obviously local Reynolds number. See, local Reynolds number is based on, it is a Reynolds number which is varying with distance. Okay, with respect to a particular distance. Let us, if you have to find a Reynolds number at this distance, that is called local Reynolds number. It is varying locally. Average Reynolds number, on the other hand, it is a total Reynolds number. That is for the whole length. It is rho v L by mu. That is average Reynolds number. Clear? So local Reynolds number is that Reynolds number which varies locally. Okay, that you can find at any particular point of time. That is called local Reynolds number. Similarly, you can find that average drag coefficient. This is the average drag coefficient. Average drag coefficient. It is equal to 1.328 by root of Reynolds number. That is the average drag coefficient. Similarly, this value for turbulent flow, it is equal to 0.07 by Reynolds number or 1 by 5. Okay. The skin friction coefficient will be equal to 0.664 root of local Reynolds number. Similarly, the skin friction coefficient, the local skin friction coefficient for turbulent flow will be equal to 0.058 Reynolds number, local Reynolds number over 1 by 5. This is how you can find the value of by Blasius equation. So Blasius equation will only be applied in the condition when the velocity profile is not given in the exam. If velocity profile is not given, then you have to use the Blasius equation. Clear everyone? Hi dear Joshi sir, how are you my dear? So Joshi sir is also awake so late like you guys. He is also very hardworking, and so I hope most of you who are from civil branch must be knowing Joshi sir. So my dear students, so this is the we can say this is how the theory of boundary layer that we have completed, and I have told you about how the boundary layer will grow and what is the different parameters for finding this, especially displacement thickness, momentum thickness, energy thickness. We have also seen how to find these different parameters. Okay, clear everyone? Is that clear to all of you? Yeah, sure, Ashish, no problem. So, my dear, let us understand this term boundary layer separation. What is this boundary layer separation? The last thing is boundary layer separation. The last topic of this topic of boundary layer, that is boundary layer separation. So, I have told you in the start of the lecture that there is a reason why the car bodies have a perfect different type of shapes. You will see if you compare the shapes of different car bodies, or if you compare the shape of an aeroplane or a car, why they have given a perfect different kind of shapes like that. Or have you ever imagined if you have seen a golf ball or a tennis ball, they will be having some kind of depressions in the golf ball. Why they are there? Why they have given there? The reason why they have given the depression on the golf ball, why they have designed the aeroplane or in that particular shape, or the blades of the aeroplane, or why the car bodies have given a perfect streamline shape like that. Why they have why they are perfectly designing those bodies like that. The main reason is boundary layer separation. One more thing, in the Venturi meter, why the divergence angle is kept below 7 degree. All these phenomena are related to boundary layer separation. Even in the case of compressor, because you are from mechanical, some of you are from mechanical background, you know that those in the case of a compression also, you study about surging, stalling, right? Surging or stalling are the two phenomena. So stalling is a phenomena in which, because of the boundary layer separation, the flow will separate from the boundary. This is a phenomena is also it is also important for boundary layer separation. Stalling phenomena. It is related to boundary layer separation. In the case of a compressor, in compressor you will be studying about surging, stalling and choking. Right? Even in the Venturi meter you study about this boundary layer separation. That is why the divergence angle is kept below 7 degree. So initially what happens when the fluid will start to flow over a surface, you will notice that the fluid particles will accelerate, or we can say the fluid particles will move with increasing velocity gradient, or pressure will try to decrease, because as you know that the flow always takes place from high pressure to low pressure. The flow takes place from high pressure to low pressure, right? Or we can say the flow will be kind of accelerated flow. Velocity gradient will be positive when the flow will take place over any surface. Okay. So initially when the flow will start over a surface, what will happen? The velocity gradient, there will be some positive velocity gradients as the flow will take place. And also as the flow will take place from high pressure to the low pressure. Generally it happens, right? The flow generally takes place naturally from high pressure to low pressure. That is a normal thing that will take place. So when this will take place, when pressure gradient will be negative, pressure gradient means negative means the flow will take place in direction of decreasing pressure. When the pressure is decreasing, the flow is taking place in direction of decreasing pressure and velocity gradients are positive. Under that condition, the flow will be attached to the surface. The flow will be attached to surface over which the fluid is flowing. The fluid will try to get attached to the surface. It will like that. Or the flow will follow the surface of that body over which the fluid is flowing. It will follow that surface of the body. But after crossing a particular region, what will happen? There will come a point when the fluid will try to separate from the boundary of that surface over which the fluid is flowing. That point is called as separation point. The point where the first rise of pressure will take place. Okay, or it is that point at which the boundary, the flow will try to depart from the boundary. What is the meaning of that? So I have told you that flow will take place from region of high pressure to low pressure. But suppose that in the direction of the flow, suddenly if pressure increases, then what will happen? Then flow will take place in the backward direction. If the pressure will increase in the direction of flow, if pressure increases, the flow will try to flow in the backward direction. This will be the direction of flow in that case. Or we can say flow reverse will take place. Reversal of flow will take place. Now this will take place under which situation? When here pressure will be more, when high pressure will be in this direction and here it will be low pressure. Under this situation, the flow will try to move in the opposite direction. It will try to separate from the boundary. Why? Because let us say we are having this surface. The flow was trying to flow like this, right, over the surface. But suddenly what happens, because separation, the flow will reverse like this. So it will try to separate from the boundary. The flow will try to separate from the boundary. That happens because when in the direction of the flow, where suddenly the pressure will increase, that will cause the reversal of the flow or flow reversal. The flow will change its direction. It will cause reversal of the flow. That is called as boundary layer separation. The flow will separate from the boundary. Now, there are conditions of boundary layer separation. There are different conditions of boundary layer separation that you have to understand. As I have just told you that boundary layer separation takes place when in the direction of the flow, the pressure suddenly increases, right? And because of that, the flow will separate because of flow reversal. Now, there is one condition which is called as attached flow. When the flow will remain attached to the surface, that is called attached flow. This will happen when velocity gradient will be positive and pressure gradient will be negative. In that condition, the flow will try to completely get attached to the surface. Like that, it will flow. That is another condition that is called as separation. Separation point, the point at which separation will start to take place. It is called separation point. Okay, that is the point at which velocity gradient will become zero. The last point is called as detached flow. Detached flow means when the flow will separate from the boundary over which the flow is taking place. Detached flow means when pressure gradient becomes positive and velocity gradient becomes negative. So what is the reason why this boundary layer separation is taking place? Because what happens when the flow will take place over a surface, the flow will when the fluid flows over a surface, it requires some kinetic energy for its flow, right? Now, after moving a particular distance, when suddenly kinetic energy will drop and the fluid will not be having enough kinetic energy, then what will happen? The pressure energy begins to increase and kinetic energy becomes to drop. That condition, when pressure energy will try to increase and kinetic energy will try to drop, that condition is called detached flow, and under that condition boundary layer separation will take place. This is the condition of boundary layer separation. So how can you suppress this boundary layer separation? Boundary layer separation can be suppressed by using some methods. That is, we can use some acceleration. We can accelerate the flow in the direction in the boundary layer region. We can accelerate the flow. How can we accelerate the flow? By using some suction method. We can use some blowers. Okay, we can supply some additional energy from a blower. We can rotate the boundary in the boundary layer region. We can increase the rotational kinetic energy. We can streamline the body. This is used for aircraft and automobiles. We can streamline the bodies in order to avoid boundary layer separation. Keeping the divergence angle to minimum. This happens in the Venturi meter. In Venturi meter, I told you that we keep the divergence angle below 7 degree in order to reduce the boundary layer separation. Okay, so this is a method we use for reduction of boundary layer separation. Clear? So now let us solve few numericals quickly. In this, which is we need to memorize. You have to memorize these two conditions. These are the conditions that we need to memorize. One second. This condition you have to memorize. That is condition for detached flow and condition for attached flow. Generally, they will ask you these conditions. And what is the point at which separation will take place? The point at which separation will take place will be this point. One more thing that you have to remember is these points you have to remember. How the boundary layer thickness will vary with for laminar flow. How it will be varying with velocity, free stream velocity. How it will vary for turbulent flow. These relations are very, very important. The formulas, this formula for drag force is important. Skin wall shear stress is important. Even this von Karman equation is important. This equation is important for the wall shear stress. If the velocity profile is this, if this is the velocity profile, then this will be the wall shear stress. Directly you can apply this formula. Okay, the formula for momentum thickness, energy thickness, and displacement thickness, these formulas are also very important. Okay, so these are all important formulas that you have to remember. Now let us quickly solve few questions because it's all, close to 1 AM. So we have to wind up the session also. So hurry up, guys. Why pressure suddenly increases? Very good question. Actually, what happens that what is the reason for boundary layer separation? It is the reason, the main reason is the pressure is increasing in the direction of the flow. It increases when the fluid particles which were trying to move over the surface, they were actually trying to fight with the viscous shear force. Okay, so they were having some kinetic energy. Because of that kinetic energy, they were fighting with that viscous shear force, and because of that, they were able to move over the surface. Again, viscosity. But suddenly their kinetic energy tends to drop. They are not able to follow the boundary. And when kinetic energy will drop, obviously, if velocity will drop, pressure will increase. So as the velocity will drop, the pressure will begin to increase. So that is the reason why pressure start to increase. When pressure will increase in the direction of motion, that means you are moving in this direction of high pressure. You never move from low pressure to high pressure. You always move from high pressure to low pressure. So then because the pressure has increased suddenly, that is why the reverse flow will take place. Okay, because of boundary layer separation. Now let us quickly solve few questions. Hurry up, because we don't have much time. We have to wind up the session quickly. Yes, the boundary layer thickness in centimeter at the trailing edge of a flat plate, which is 15 centimeter wide and 45 centimeter long, placed longitudinally in a stream of oil of relative density 0.925 and kinematic viscosity of 0.9 Stokes, flowing with a free stream velocity of 6 meter per second. So free stream velocity is 6 meter per second. The viscosity, kinematic viscosity is equal to 0.9 Stoke. As you know that 1 Stoke is equal to 10 to the power minus 4 meter square per second. Okay, they have also given the so you have to find the boundary layer thickness. Firstly, you have to check whether it is laminar flow or not. Okay, because if you have to find the boundary layer thickness, you have two formula. One formula is this 5 into x by root of Reynolds number, and one formula is this 0.371 x Reynolds number over 155. This formula is for turbulent flow. No, it is not for JEE exam, it is for GATE exam, my dear. Okay, this is for laminar flow. Firstly, we have to figure out whether it is laminar or turbulent flow. We don't know about it. So how can you find it? We have to find the Reynolds number for that. So Reynolds number will be equal to rho V U infinity into x by nu. Or we can simply say V infinity into x by nu, because they have given the kinematic viscosity. So you have to firstly find the Reynolds number. So find Reynolds number. They have given the free stream velocity. They have given the length also 45 centimeter. Find Reynolds number. This will be V infinity, that is 6 into 0.45 meter divided by 10 power minus 4. Find the Reynolds number quickly. Hurry up. Yes, everyone, be quick. So firstly, you have to find the Reynolds number. After finding the Reynolds number, you have to put that. Yes, come on, be quick. You will find Reynolds number, that will be 3 into 10 power 4. Okay, because this Reynolds number 3 into 10 power 4, it is Reynolds number that you have find is 3 into 10 power 4. It is less than 5 into 10 power 5. That is, it is a laminar flow, and because it is laminar flow, it is confirmed. You can use the formula. This formula you can use, that is delta will be, boundary thickness will be 5 into 0.45 divided by root of 3 into 10 power 4. You will solve it. You will be getting is the answer as 11 point. Yeah, that will be 1.9 1.29 centimeter. Are you getting this value 1.29 centimeter, everyone? Yes? Is everyone getting the value as 1.29 centimeter? Please tell me. Is it clear to all of you? So hurry up guys, hurry up. We have to solve many questions today. Yes. For this session I have taken 7 questions because it is 1 p.m. Yeah, definitely I will make a video on revision of all the important formula of fluid mechanics. I will make a video on that, don't worry. Clear? Yes, tell me. Now solve this question. The ratio of the displacement thickness to momentum thickness for linear velocity distribution in a laminar boundary layer along a flat plate is. Is everyone getting the answer 1.29 centimeter? 1.29 centimeter is getting or not? Okay, because you have to find the boundary thickness in centimeter. Then solve this question. Hurry up, everyone. I have told you how to find what is the meaning of linear velocity distribution. In terms of boundary layer, what is the meaning of linear velocity distribution or linear velocity profile? Linear velocity profile is u by u infinity is equal to y over delta. This is a linear velocity profile. Linear velocity profile. So we will be using this linear velocity profile to find the value of displacement thickness and momentum thickness. Hurry up. Yes, be quick, my dear students. Hurry up. The ratio of displacement thickness to momentum thickness for linear velocity distribution in a laminar boundary layer along a flat plate. I have solved this question actually in this class. In this class, I have solved this question. I have told you that displacement thickness will come out to be delta over 2 and the momentum thickness will come out to be delta over 6. You just have to use displacement thickness is equal to 0 to delta of 1 minus u by u infinity dy. If you integrate this by putting this velocity profile, you will be getting this value as delta over 2. Similarly, the momentum thickness is equal to 0 to delta u by u infinity 1 minus u over u infinity dy. Okay, so this value will be delta over 6. So the answer will be option D, right? Because the ratio of displacement thickness to momentum thickness is called shape factor. So it will be equal to 3. Very good, very good. Next question. Next question, hurry up guys, hurry up, be quick. For a laminar flow over a flat plate, if free stream velocity of the fluid is 10 meter per second, the boundary layer thickness near to the wall is 10 mm. Determine the wall shear stress. For a laminar flow over a flat plate, if free stream velocity of the fluid is 10 meter per second, boundary layer thickness near to the wall is 10 mm. Determine the wall shear stress. I have told you the velocity profile is given here. The velocity profile is given here. For this velocity profile, I have told you the direct formula for the wall shear stress. If you remember this thing. So you have to use the direct formula, you will get the answer. Hurry up, come on guys, be quick. Yes. Tomorrow is the last class of the late night series on fluid mechanics. Tomorrow we'll be studying about Pelton turbine. So tomorrow will be the lecture on hydraulic machinery and that is on Pelton turbine. Okay. Yes, come on guys, be quick, hurry up. The velocity profile is u over u infinity is equal to 3 by 2 y over delta minus half of y by delta q. You have to find the wall shear stress. Wall shear stress is equal to mu du by dy at y is equal to 0. This is the wall shear stress. I told you the formula. Even I told you the direct formula for the wall shear stress if this is a velocity profile. If you remember the direct formula, it is mu 3 by 2 u infinity over delta. I told you this formula. Remember that? I have told you this formula in the class only. So u will be equal to u infinity 3 over 2 y over delta minus half of y over delta cube. Okay, so du by dy will be equal to what? Du by dy at y is equal to 0 will be u infinity times of 3 by 2 delta minus half of 3y square by delta cube. At y is equal to 0, this term will be 0. So ultimately we will be left with this term. So this the wall shear stress will come out to be this. We just have to put all the values here. Viscosity is given 0.863 poise. 0.863 poise, which is 0.0863 Pascal second. Okay. Free stream velocity is given. The boundary layer thickness you have to find. The boundary layer thickness, sorry, it is given 10 mm. Okay, that is 10 mm. So delta is 10 mm. It is 10 into 10 power minus 3 meter. Okay, so everything is given. Just put all the values. The free stream velocity is 10 meter per second. You will getting the answer is option B, 129.45. Okay, clear everyone? Is it clear? You are a little bit confused about Reynolds number. Do not get confused. Akash point is very simple. Reynolds number for pipe flow, for laminar flow it is less than equal to 2000. For turbulent flow it is greater than 4000. For flow over a flat plate, the Reynolds number is for laminar flow is 5 into 10 power 5. For turbulent flow it is 10 greater than 10 power 7. Okay. Okay, so I think we have 3-4 questions more left, but I think we'll be solving those questions tomorrow because it's already 1:05. So I don't think I will be extending the lecture much. Okay, so rest of the question, if you are not having any problem, we can solve tomorrow. Okay, or we can solve it because it's 1:05, and if we can extend the lecture, it will go up to 1:15. Okay. So we are having few more questions. Let us solve this question first. 2 questions are more left. We can solve it later on. If delta 1 and delta 2 are boundary layer thickness at a point from leading edge, at point from the leading edge on a flat plate, when the Reynolds number are 100 and 256, then delta 1 to delta 2 will be how much? Oh, that is when you see in some textbook they are using Reynolds number as 2300. See, it is basically given in some textbook, but actually it is 2000. Because in some standard books they have given the value as 2000. Okay, so for laminar flow Reynolds number is less than equal to 2000. In some books you will find it as 2300 they have given, but approximately they will be taking that as 2000. Do not get confused about that. Okay, solve this question as last question. 3 questions I will take tomorrow. This is 1 question I will take tomorrow. Okay, this is 1 question I will take tomorrow. This is from drag force concept, and this question I will take tomorrow. These 3 questions I will take tomorrow. Okay, let us solve this last question. Come on everyone, be quick, hurry up. Let us take this as our last question. Hurry up. If delta 1 and delta 2 are boundary layer thickness at a point from leading edge on a flat plate, when the Reynolds number are 100 and 256, then ratio of delta 1 to delta 2 will be. Any clue how to solve this problem? Yes. Kamran has given 1.6, Vikas Yadav B, Dharani has given B, Vaibhav Yadav B. Everyone tell me what is the answer. The Reynolds number is given as, Reynolds number 1 is, let us say 100, let us say Reynolds number 2 is 256. You have to find the ratio of delta 1 by delta 2. You know that Reynolds number is less than 5 into 10 power 5. Because it is less than 5 into 10 power 5, it is a laminar flow. And for laminar flow, Reynolds boundary layer thickness is inversely proportional. It is equal to inversely proportional to root of Reynolds number, right? For laminar flow, so we can say delta 1 by delta 2 will be equal to root of Reynolds number 2 by Reynolds number 1. That will be root of 256 by 100. Very simple. It is 1.6. Are you getting the answer, everyone? Yes, exactly. Okay, so with this I would like to conclude the session because it's 1:08 and it is quite late. So we cannot generally extend the class more than that. So 3 questions I will be, let us say this question as homework. You can solve this question as homework, okay, for tomorrow's class. In this question, they have given the mean drag coefficient for a laminar boundary layer over a flat plate was 0.015. If all the flow factor remains same and length of the plate is decreased to 1/4 of original value, then drag coefficient would be equal to. So they have given drag coefficient 1 as 0.015, let's say. The length of the plate is decreased, that is L2 is equal to L1/4. Length is getting 1/4 of original value. You have to find the value of drag coefficient 2, average drag coefficient 2. Okay, so this question you can take it as homework, and last 2 questions that I have not taken, I will take it tomorrow. Okay, there will be x in numerator. Where numerator? See, doesn't matter if it is x, it is not x in the numerator, it will be x in the numerator. So how does it matter? Because we have to find the relation of boundary layer thickness and Reynolds number. There will be x in numerator. It is delta boundary layer thickness is equal to 5 into x by root of Reynolds number. But here we have to find the Reynolds relation between boundary layer thickness and Reynolds number, not between the distance from leading edge. Okay. So you have to solve this question as homework and you have to give the answer tomorrow. Okay. Before we conclude the session, we have to tell you about some paid courses which currently we are providing on Gradeup. Gradeup and RankUp are the paid courses. I think these are not useful for you now because GATE exam is very near now. But Vision 2022 is a paid course which you guys you can be interested, because if anyone is preparing for GATE and Engineering Services 2022 exam, then you can join our Vision 2022 paid course. Okay, we are also about to start our Vision 2022 paid batch 3. Okay, so if anyone is interested for joining our paid course of GATE and ESE 2022, you can join Vision 2022 paid course. This is a list of the toppers who have got selected from Gradeup. They have joined our paid courses and they have got selected. So you can take basically inspiration from them and you can also be a part of Gradeup. Okay, Gradeup Super basically, if you guys know that it is one subscription to access all the paid courses. Just by one subscription you can access all the live courses, whether you are preparing for GATE exam or ESE exam, whatever courses we are having, you can join those courses with just one Gradeup Super. Also, Gradeup Super gives you access to our Gradeup Green Card, which again gives you access to all our test series of different exams. Okay, so you can take the subscription of Gradeup Super today. Also, if you have Gradeup Super, you can access to a preferred live course, whether it is a 3-month course, 12 months, 18 months or 24-month course. It's totally up to you what course you want to enroll, because with Gradeup Super now you don't have to give subscription to don't have to take subscription of each and every courses. Okay, individually you can join all the courses with just Gradeup Super. So that is all in today's session. Tomorrow is the last class. Tomorrow is last lecture of FM. Okay, in late night series, tomorrow the last lecture that will be on Pelton turbine. Okay, Pelton turbine is also a topic from which questions from hydraulic turbine. This topic is very important, Pelton turbine. So I will be telling you Pelton turbine and specific speed of turbine. This topic will be covering specific speed, Pelton turbine, unit quantities. All these things will be covering in the last lecture of FM. Okay, so thank you so much for joining me for today's session. And 2 questions I have not taken. 1 question I have given for homework. 2 questions we'll discuss tomorrow. Okay, so thank you so much for joining me for today's session. If you have liked this, please hit the like button. Okay, and also you can subscribe our channel and press the bell icon if you have not done yet, so that you don't miss any videos of Gradeup. Okay, so you can also share this session to your friends who are preparing for GATE exam or GATE 2021 exam. Okay, so that they can also join these classes. Could you please upload the timetable of classes again? Baldev, the timetable of the Vision this late night series has been uploaded in our Telegram group, that is Gradeup ESE and GATE /ME preparation. You can join our Telegram group. The link of the Telegram group is given in the description. You can join that. Okay. So thank you so much for joining me for today's session and have a very good day. Thank you everyone. I will see you tomorrow at 11 p.m. Thank you everyone.